Alright, so in the last class we had started with phasors and the phasor diagram. So phasors are basically the vector quantities, the rotating vectors. Here we had EMF and the alternating current which rotated, and we using the phasor diagram we could actually predict the position, whether current is leading your voltage, is leading your current, or what is happening. So yes, Khalid, what was the phase difference between current and the EMF in case of circuit containing only resistor?
Yes, ma'am. Zero.
Zero. Means if they were in the same phase. Exactly right. Fine. They both were in the same phase. And Z, what was the phase difference between both of these when they had only the inductor connected?
M pi by 2.
Pi by 2. But which leaded which?
M current leaded voltage.
Current leaded voltage. Alright, let's just quickly see. One last circuit was left, then we could start with the LCR circuit. So current AC circuit containing only resistors, E is equal to E naught sine omega t. Current is also I naught sine omega t. Both are in the same phase, that can be represented from here. Alternating current containing only inductor, E is equal to E naught sine omega t. Current is I naught sine omega t minus pi by 2. Or you can write this equation as E naught sine omega t. You can write this as E naught sine omega t plus pi by 2. That will show you that this is leading. Or you can write I naught sine omega t minus pi by 2. That shows that current is lagging. So XL was a new term that was introduced. That was the resistance in case of a circuit containing only inductor. This was the representation. So that shows what? XL is basically resistance. And resistance value is what? The resistance, you can write it as XL, which is omega L. One last circuit that was left, what? AC circuit. Containing only a capacitor. Here it means a single capacitor has been connected with the rotating EMF coil. So capacitance will be C. Fine, class. So a capacitor in a DC circuit, you know, ammeter is connected, battery is there with EMF, a tap key is there, and you find all the values. In AC circuit containing only resistor C, E, let's say this is E naught sine omega t. Let's start from here only. So E is equal to E naught sine omega t. Now see, due to the continuous charging and discharging of the capacitor plates, no, a continuous but alternating current, continuous though, but an alternating current exists in the circuit. So potential difference is what? Potential difference is basically this E, which is E naught sine omega t, and V is equal to Q divided by C as well. From here, you can write the value of Q as CV. So V is E naught sine omega t. So Q becomes C into E naught sine omega t. This is Q is equal to CV. Now, current at any instant will be given how? Differentiation of charge with respect to time. This is an easy derivation, a very short derivation. So instead of charge, you can write differentiation of C epsilon naught sine omega t. This is equal to what? Omega is a constant, so that will come out C epsilon naught, not epsilon naught, sorry, E naught. These are also constants, and we'll be having cos omega t left. So equation of current becomes what? Omega C E naught sine omega t. No, sorry, cos omega. This is E naught cos omega t. Now from here, I'll write omega c E naught as the peak value. If you write the main equation, I is I is equal to what? I naught cos omega t or sin omega t, both these are valid. You can write it as cos omega t right now. So if you compare these, here you are getting I naught, here you are getting omega c E naught. So what do we can write this as one more thing as well. To make it in terms of sine, I have to write this as what? I naught sine omega t plus pi by 2. Then I can write sine. Because there's a difference between them, that is 90 degree. So to change it, you can add 90 degree in the sine value to get the value of cos. So here, this is the equation. And E is equal to what? E was equal to E naught sine omega t. Now plus pi by 2 is coming here over here. So what's the conclusion? Which is leading what by which angle? Anyone?
Current is leading voltage by pi by 2.
Pi by 2. Perfect there. Current is leading voltage this time by 90 degrees. Earlier, current in case of inductor, current lagged behind the EMF by 90. Or you can write this equation as E is equal to E naught sine omega t minus pi by 2 to show that EMF is lagging by 90 degrees. If you want to show it graphically or using the phasor, see. And as I've asked you people in the last class as well, I request you all to draw this by two colors. See, let's say EMF value is this. This is EMF. Now, EMF is lagging behind the current. It means EMF is lagging behind the current by 90 degrees. So, if when E is at 0, current will already be at its 90 degrees value. See, this lesson is defining that this is there's a difference in the amplitude. Don't go by the lowering sign, go by this angle from where it has started. Where EMF is at 0, current has already reached its maximum because current is ahead by 90 degree. This way, current will go. Here the difference is pi by 2. This red one is current. Here the peak value is I naught, here the peak value is E naught. So EMF, let's say EMF is here, E naught. This is making angle omega t, whatever. Now current is what? In case when we had drawn it for the inductor, current was here, showing that it is 90 degree behind, lagging behind. Now this is 90 degree ahead. So here I'll draw the current. This is the angle that is 90. One last fact from here as well, before you start noting it down. What was here value of I naught? See, value of I naught, if you compared both the equations, I naught came up to be what? Omega c E naught, means EMF. Now, if I write this in the denominator, or let me just show you. If I bring this in the denominator, no. This can be written as 1 by omega c. 1 by omega c can be written. Agreed or not? See, if it is 1 by omega c, then only omega c will go up, which will be equal to this. I have just brought this omega c into denominator, and to bring in denominator, I have to bring it in the denominator's denominator. Then only this will go up and this will be. Is this clear? Is this point clear to all of you? Why am I writing? All right. Anyone is having any doubts, ask me. Now from here, if you apply your Ohm's law, what's the resistance that you're getting? From here, if you notice, This is the resistance. This term 1 by omega c, this is what? 1 by omega c, this is xc, which is known as the capacitive reactance. In case of a normal circuit with a resistor connected only, the opposition was offered by the resistor. It offered such a huge resistance. In case of inductor, you have XL, inductive reactance, to do the functions of the resistor. In case of circuit containing only capacitor, you have what? You have XC, that is the capacitive reactance. This does what? This does the function of opposition. This is the opposition offered by the capacitor to the flow of AC through it. Fine. The work of resistance, that is, this is known as capacitive reactance. So XL was omega L. XC is not omega C. It is 1 by omega C. Keep this in mind. XL was 1 by omega L. Once you note it down, we'll make a comparison also. So at least we'll write down one conclusion. XC, if this can also be written as 2 pi nu C. Because this is equal to what? This is equal to omega C. One more thing, class. XL was directly proportional. See, if you see XC and frequency, both are inversely proportional to each other. So if you plot a graph between XC and frequency, the graph will not be a straight line this time. It will be a hyperbola this time. All right, this is what it is about your capacitive inductance, capacitive reactance. Here your IRMS, if you write, IRMS is equal to I naught divided by root 2. I naught is what? Here I naught is E naught 1 by omega C, root 2. And E naught by root 2 is what? ERMS. So that becomes ERMS by 1 by omega C or ERMS by X. All this. We'll do a conclusion also. We'll do a conclusion, then we'll do certain questions before starting with LCR circuits. Just note down these points. See, regarding the conclusion, let's just discuss one thing. If a circuit is there which has only a resistor connected, then EMF is given by E naught sine omega t. Current is given by I naught sine omega t. Fine. E naught sine omega t, I naught sine omega t. This directly shows you what? That both are in the same phase. E and I, these are in the same phase. I naught is equal to E naught by R. When you have a circuit which contains only inductor, that time EMF is E naught sine omega t. Current is what? I is equal to I naught sine omega t minus pi by 2. This means that current lags and voltage leads. By how much? By 90 degrees or pi by 2. And I naught is given by E naught by XL, which is equal to E naught by 2, not 2 pi, omega L. And further, omega can be written as 2 pi nu L. So this is omega L. L is the self-inductance. Self-inductance is exactly what you studied in EMI. If a circuit contains only capacitor, then you have E as E naught sine omega t. Current is I naught sine omega t plus pi by 2. This shows you what? This time current leads, voltage lags. By how much? 90 degrees or pi by 2. I naught is equal to E naught divided by XC, which is equal to 1 by omega C. And now you can keep on performing the modifications. Performing the modifications means what? RMS value in terms of linear frequency 2 pi nu and all these values. So this is the conclusion of resistance circuit, inductance circuit, capacitor circuit. We'll do 2 questions, 1 or 2 questions we'll practice from this, because from here the questions are very easy. Questions from this part are very easy. We'll do those questions. But then we'll start with a circuit which has inductor, capacitor, and resistor together. LCR circuits. First we'll do LCR, then we'll do the other types of circuits which are there. So note down this page, then I'll give you question. Right, Zed. What did your inductive reactance come? Also type in that. Others also answer. Zed has found the value of IRMS. Last 1 minute and we'll discuss. Zed. Right answer. Let's discuss. The answer is coming. Let's discuss it. Then you people will try the next question that I'm giving. Inductance is given to you as 25 millihenry. So this becomes 25 into 10 to the power minus 3 Henry. What is it? Is connected to a source of 220 volts, means ERMS is 220 volts. When nothing is mentioned, no, and it is written, it is connected to a source of this with frequency this. Assume that this is the RMS value given. And frequency is also given. Frequency is given as 50 hertz. Here you have to first find out the inductive reactance. Inductive reactance XL is what? Omega. Omega is not given. We'll convert it in terms of frequency. 2 pi nu L. 2 pi is 3.14. Frequency is 50. L is 25 into 10 to the power minus 3. So 3 into 25, 7 something it will come. Yes, 7.85. This is the XL's value. Now you have to find out IRMS value. IRMS is ERMS divided by XL. So ERMS is 220, XL is 7.85. This will be around 28.03 amperes. Like this you have to solve. Whatever you studied in current electricity, formulas are the same, just you have to replace terms in terms. If I naught was asked, then you would use E naught divided by XL. Concept will remain the same. Like this. I'll give you one more question, try that. And whoever gets the answer, send me this on the group. Send me the solution on the group. I think by now only Zaid has got his answer, no? Others have not written. All of you quickly do this question and send me your answers on the WhatsApp group. Zaid, click the pic and send me on the group. Others also try. At least frequency you can tell. L is given, XL is given. Nu you are asked to calculate. See class, how will we solve this? It says a coil has an inductance of 1 Henry. So L is 1 Henry. Fine. You people have also not got any answer. Khalid, Salman. Khalid,
Yes, teacher, I'm
Yeah,
typing
I-
now. Answer.
should I wait for 2 more minutes? Whose answer is this? Okay, Samaira's answer. This is frequency. Yes, frequency is correct. Right. Okay, Salman has answered. Fine. Welcome. Okay. So let's discuss this. See, L is given as 1 Henry, XL is given as 3142 ohms, 3142 ohms, this much is given. Frequency is unknown. XL is equal to omega L, which is equal to 2 pi nu L. From here, frequency will be equal to XL divided by 2 pi L. So frequency's calculation is easier. Frequency will be equal to what? XL is 314 divided by 2 into 3.14 into L is 1. So when you solve this, you will get your answer as 500 hertz. Is this clear? Hania, is this clear?
Yes, ma'am.
All right. If you are having any doubts, anyone, not only Hania, anyone is having any doubts, ask. So Excel, from here you can calculate. Second part C is that what should be the capacity of a capacitor which has same reactance at that frequency. Means capacitance is now unknown. Capacitance, you know what is capacitance? C is unknown over here. It says if XC is equal to XL, then what is the value of C? So if XL is equal to XC, this will be, it means this is also equal to, this was the number, no? Yes, 314, this much. So XC is equal to what? XC is equal to 1 by omega C, which means 1 by 2 pi nu C. So C is equal to what? Exactly. C from here, this will be equal to 1 by 2 pi nu, and we will be having XC over here. Just interchange these two. So when you put this, you get the value 2 into 3.14. Frequency kitni thi? 500. And XC is 314. This much. When you solve this, you will get your answer as 0.11 microfarad. Capacitance was on. All right, just note down the solution. Then we'll start with LCR circuits. So do one thing, class. Take a break of 5 minutes. Then I'll start with series LCR circuit. Get yourself freshen up because LCR circuits, this is one of the major important topics of this lesson. So after 5 minutes, I'll start with the class. All right, class, let's begin. See, LCR circuit means what? L means inductor. So inductor is connected in a circuit. Inductor is connected with inductor. All of you are here, no? Yes or no?
Yes, ma'am.
Others? There is your, what about you both? Khalid, Salman?
Yes, ma'am. Here.
All right. Fine. So inductance, this is L. Then C. C means capacitor connected, which has the capacitance C. So LC and R means R stands for a resistor with the value capital R. So again, one more thing here will be the moving coil galvanometer, with which the whole circuit will. We have seen all these individual circuits. In individual circuits, what happened? Current and voltage were in the same phase. Here, the voltage leaded current by pi by 2. Here, the current leaded the, here the voltage leaded the current by pi by 2. Here, the current leaded the voltage by pi by 2. This is what we have studied, and let's say this is E naught sine omega t. This much we have studied. Now, if I talk about the voltage, across this resistor, current is I. Let's say current of this whole circuit, the current of this entire circuit is I. So if current is I, resistance is R. Hania, can you tell me what will be the voltage across this? Resistance is R, current is I. So what will be the voltage? Yes, Hania. Resistance, current, voltage, what's the relation between them?
V is equal to IR.
Exactly, V is equal to IR using Ohm's law. V is equal to RI, yes, V is equal to IR. So voltage across the resistor will be given by I into R. Resistance of this, Salman, what do we take the resistance of the inductor? Only inductor. Yes, Salman? Are you there, Salman? No, I don't think the Salman is over there. Zaid, can you answer? What's the resistance that we consider for this inductor? Yes, Zaid, say.
Ma'am, inductor like XL.
XL, yes, right, XL. So XL acts as the resistance for the inductor. So if XL is the resistance, current is I. What will be the voltage across the Z?
I don't.
Yes, say Z. See, resistance, you are saying resistance is XL. Current in the circuit is I. So voltage will be what? Try Z. Whatever you're saying, say it. It's okay, say it.
I into omega.
I into omega L, or simply XL into I. Correct. XL is the resistance, I is the current. So voltage across the inductor is XL into I. These individual questions can also come. Samaira, what's the resistance across a capacitor in an AC circuit? Yes, Samaira. Resistance. The way XL is the resistance across inductor for AC circuit. What's XC? Yes. So if XC is the resistance, current is I. What will be the voltage across this capacitor?
XCR.
XC. Exactly. This will be XC into I. So voltage across resistor is this with these much details, voltage across inductor is this which with this detail, and voltage across capacitor is this with this much detail. Now, one more thing before we proceed with it. So this much is clear. What's the voltage across all these three? So now we have combination of all these. We have a combination of all these circuits. So how will our phasor diagram be? If you have to draw a phasor diagram for the same. Because right now you're not aware of which quantity is leading which quantity. So every time you need not draw this circle. Circle can be avoided as well. Mainly you have to draw these graphs. These lines here. Now let's say EMF. Let's say EMF is fixed. Or let's say this is the voltage across the resistor. Remember for the resistor EMF we have drawn in this way only. We are just considering the resistor voltages right now. So for the resistor voltage we have drawn in this way only. Yes. Now for the capacitor, for the case of a capacitor, the recent case which we have done, there what happened? Voltage lagged behind. For the capacitor, see voltage is lagging behind by 90 degrees. So here also in this diagram also we'll draw the voltage like this. This is lagging behind. This does not mean that the magnitude is less or the magnitude is more. This is not this is not in connection with the magnitude. It simply means lagging behind. It is just about the phase. These are phasors. These are not simple algebraic quantities. Then what about the voltage in case of inductor? Voltage in case of inductor, it leaded by 90 degrees. So when you draw the phasor diagram for this, here this will lead by VL. This is the voltage across inductor. Now how to solve this? See, two things can occur. One thing that can happen for the resultant is that, remember your parallelogram law. If you had your parallelogram law, then what would you do? You resolve two vectors first, you solve two vectors at a time, then with the resultant you solve the third quantity. Here also both the things will occur. It can happen for solving VL and VX. It can happen VL is greater than VC or VC is greater than VL. So when you have VL greater than VC, then consider VL minus VC. If you have VC greater than VL, then VC minus VL will be taken. Otherwise, one of the answers will come in negative. So you can easily directly avoid negative, whichever quantity is greater, that you can use. So this is what? This is your phasor diagram. Now, if VL minus VC is the case, then your resultant will point here. This will be the line for the resultant. This will be VL minus VC. So what will be left? Just this much is left. VL minus VC will be left and VR will be left. If VC is greater, then here downwards will be the resultant. If VC is greater, then this will be VR. This becomes VC minus VR. This way here it will have the result. And the way you solve parallelogram like that. Now, before beginning to these details, know about these two cases. You have to know about the impedance triangle. Impedance triangle is helpful in the calculation of the impedance. See, impedance is what? The way resistance was there in case of the resistor circuit. XL was there in case of the inductor circuit and XC was there in case of capacitor circuit. So all these were what? R, XL, XC were the individual resistance only, the opposition that occurred. So if you combine all these three in this circuit, the net resistance that you get, that is represented by Z, which is the impedance. So it's actually a combination of all these resistance. And how it's a combination, what is the formula, that let's see with the first help of an impedance triangle. So impedance triangle is basically a triangle with this as Z, which is the impedance, this as either XL minus XC or XC minus XL. Here we are only considering the resistance, and this is for the resistance. R is fixed, Z is the resultant, XL minus XC can happen and XC minus XL can happen. Let's do one case at least. Let's say this is, let's do it case wise. Case one means XL is greater than XC. So here if your XL is greater than XC, this means what? XL minus XC will be considered, VL minus VC will be considered, all these things will be considered. Fine. So if this side represents your resultant EMF, this side represents your VL minus VC, and this side represents your VR. VR is what? Voltage across resistance. VL is what? VL minus VC is net resultant voltage across both inductor and capacitance. So if you using your Pythagoras theorem, you have E naught square equal to VR square plus VL minus VC whole square. So E naught becomes equal to what? One more thing you can do. E naught square, you can do one more thing, that is VR was what? I think Hanya had answered this. VR was equal to I into R. So this becomes I naught into R whole square plus VL was what? VL was I into XL minus I into XC whole square. I'm taking naught because I have considered here the peak value. So from here, what do we have? We can take I naught common. I naught square is coming common from all of these. So if you talk about I naught whole square, here I naught whole square can be taken common. What is left? R square plus XL minus XC. This is left from here. Now, bring this I naught in the denominator. Or if you, instead of bringing this I naught into the denominator, let's interchange these. Let's write the value of I naught square. Let us bring this in the denominator. Then the calculation will become much easier. I naught is what? I naught will be equal to E naught. Square will get cancelled, and this will be having under root. That becomes R square plus XL minus XC. Now compare it with Ohm's law. Ohm's law is what? I is equal to V by R. Current, voltage, resistance, impedance. Got it? This is what is meant by impedance. Z is equal to under root R square plus XL minus XC whole square. Here. Whole square. This is what is meant by impedance. Had it been the other way, case 2, if we talk about case 2 where XC was greater than XL, so VC would have been greater than VL. There you will get the same exact answer. Where will be the difference? Z will still be equal to under root R square. But here you will have XC minus XL whole square. I'm writing fast, so it may happen you can get confused between L and C. So just ask me wherever you have confusion, whether it is C written or whether it is L written. So if you have case 2, this will be your answer. Here what will happen? VR will be here, but resultant of both these will be here, VC minus V. In the above part, above it will go. In the impedance triangle also, this will be Z, this will be XC minus XL, this will be here. Like this you have to consider. This right angle triangle is called impedance. And what actually is Z? Z is the resistance. Z is the resistance of this LCR circuit, series LCR circuit. All these three are connected in series. So this is actually the effective resistance. This is basically the effective resistance of the series LCR circuit. So it's a resistance that will oppose the flow, which opposes or impedes the flow of current through. Whatever work XL did in case of inductance circuit, whatever work resistor does in case of only resistance circuit, whatever work XC does in case of only capacitor circuit, you have what? You have the value as what? You have the value as Z in case of all the combined LCR circuit. From here, you can do one more thing. From this impedance triangle, you can find the value of tan theta, which will give you the phase angle. Let me tell you. See, both the case sets to simultaneously, then you will be able to make a comparison. This is Z, this is R, this is what? Let's say this is XL minus XC, this is XC minus XL, Z, R. This is the phase angle. Phi is what? This is the phase angle. So tan phi here will be equal to what? XL minus XC divided by R. And from here, tan phi will be equal to XC minus XL divided by R. Now, this depends on whether which is greater, inductance reactance is greater or capacitive reactance is greater. Fine. Now, if your inductive circuit is greater, means inductive reactance is greater. If this is the case, this is the case, here what will happen? Even if you find out cos phi from here, cos phi will be equal to what? Base by hypotenuse, R divided by Z. Here, if your XL is greater than XC, the type of circuit that you obtain, this is called as an inductive circuit. Because inductance is dominating over capacitance. So you will say this is actually C class. Wherever you get confused now between C and L, please ask me then and there while writing, whenever you write. So series circuit is said to be what? Series circuit is said to be inductive. But if this is the case, here also cos phi will be equal to R by Z. But here if XC is greater than XL, so you will say your circuit is a capacitive circuit. So either inductive or capacitive. So what about this resistive circuit? Resistive circuit is only possible if XL and XC are equal to each other. Then only you will have VL equal to VC, and here there will be no phase difference. That is what we have studied. There is no phase difference in case of purely resistive circuit. Then you can say your series LCR circuit is also purely resistive. This will say LCR circuit is purely resistive circuit. So you can directly use Z now in this circuit, E naught divided by Z. For the whole LCR circuit, the way you use resistance, the way you use XL, the way you use XC, E naught by Z, or you can write IRMS equal to ERMS divided by Z. Simple Ohm's law you have to apply, but in different aspect. So I just concluded one more time. Last time I'm repeating, I've repeated so many times. I'm repeating it last time. LCR circuit means inductor, capacitor, resistor, all three are connected. VR will be equal to IR, VL will be equal to XLI, VC will be equal to XCI. But these are all different individual quantities. When you have all these three together, then there has to be a net effective resistance for the whole circuit. That is known as impedance, whose derivation you can do with the help of an impedance triangle. Now, phasor diagram depends on whether this is the case or this is the case. If this is the case, draw the resultant here. If this is the case, draw the resultant here, whichever is dominating. That you will see when we'll do questions. The derivation of impedance is done with the help of impedance triangle. You get the fact under root R square plus XL minus XC whole square. it can be Xc minus XL whole square if capacitance is greater. If such a case is there where capacitance is greater, you say it's not a capacitive, not a capacitive, it's actually capacitive. Not capacitive. This is capacitive circuit. Inductive, resistive, capacitive circuit. From this impedance triangle, you can find the value of tan phi, cos phi, sin phi, whatever is required. And using Z as a normal whole complete resistance of the circuit, you can find out the values of I naught, IRMS, the way you have been using it. Any doubts till now?
No, teacher.
Clear to others as well?
Yes, ma'am.
Yes.
All right, so note it down. See, for this question, you have to determine the impedance of LCR, series LCR circuit. It's a reactance C. Reactance of C means reactance of capacitance. That is capacitive reactance. Capacitive reactance is 250 ohms. And reactance of L means inductive reactance of L. Both these are mentioned. R is mentioned as 40 ohm. So from here we can see XC is greater than XL. Z will be equal to what? R square under root R square plus XC minus XL. This is which will come first is determined by this. So as to avoid negative. So this becomes what? 40 square. Plus this becomes 250 minus 220. This will be 30. So 30, 40, answer will be 50. We have to form Pythagorean triplet. That becomes 40 square plus 30 square under root. This is equal to 50. Impedance, so this will be 50 ohms. This is the answer. 60. No, 40, 30, these are Pythagorean triplets, no? 40, 30, 50. This will be 50 ohms only. Or even if you expand it, that will be under root 1600 plus 900. So that will also be 50 ohms. Note down this question, then one or two questions more. In any question, if XL and XC are not given and instead capacitance or inductance are given and omega or frequency is mentioned, then do convert. XL, write it as omega L or 2 pi nu L. Write XC as 1 by omega C or 1 by 2 pi nu C if these are not directly mentioned. Try this question. This is 4 ohms, this is 4 ohms, this is 45 ohm. ERMS, this is ERMS. Whenever any value is written like this, no, along with the source of AC, this makes it ERMS. Find out what will be the readings in the voltmeter and the ammeter. C class over here. XC is written as 4 ohms. XL is written as 4 ohms. Resistance is given as 45 ohms. Z voltage will be 0 and the current 2 ampere. Yes, exactly. Right answer. So what's the impedance coming there?
The impedance is 90.
90?
Sorry. Ma'am, 45.
45. Yes, yes, yes. Impedance is 45. That's how you got 2 ampere. 90 divided by 45. Correct. So Z is what? Z is under root R square plus. Now, which will come before, which will come after it? See, both are equal. So here you have 4 minus 4 whole square. You can write any of these. So this becomes what? Here XL is equal to XC. Now Z, through this question, I'll relate one more topic. That's why I've given this question. So I hope everyone has at least tried this. Z is what now? Z is under root R square. That is 45 whole square, which means 45 ohms. Because this got cancelled. Now, for IRMS, value of ammeter will be what? Alternating current, IRMS value. So, IRMS will be ERMS divided by Z. ERMS is this one. ERMS is 90 volts. 90 divided by 45 gives you 2 ampere. And you have reading of voltmeter. So see, for the reading of voltmeter, it's what? It's basically resistance multiplied by current. What's the net resistance? XC minus XL or XL minus C into current, IRMS, whatever you choose. See, ultimately 4 minus 4 will give you 0 only. So voltage will be 0. Reading of voltmeter will be 0. This will be 4 minus 4 into whatever. Reading of voltmeter will be 0. Just quickly note down the solution. I'll share one topic with you right now. A very, very small topic. Just note this quickly.
Ma'am, why there is no flow of DC current through a capacitor?
DC blocks it. Whenever you have direct current, no, through it, it blocks it. That's the property of a capacitor. So that's why we do not have it. We just have alternating current.
Okay.
Others have also written apart from Sumaira. Oh, C class. What I was trying to tell you is this condition when XL is equal to XC. Here in this question, what did we have? We had XL was 4 ohm and XC was 4 ohm. So when this XL and XC both are equal, we get a condition which we call as resonance condition. Resonance condition of LCR series circuit. Resonance condition. Resonance condition means XL is equal to XC. So in the exam, you can be asked, what do you mean by the resonance condition of series LCR circuit? Calculate its resonance frequency. So resonance condition is meant what? It is said when current through it has its maximum value. This is one of the conditions that comes through it. This is for your identification, for you from your examination point, from your calculation perspective. But in actuality, what happens? What is the resonance condition? So a series LCR circuit is said to be in resonance when current through has its maximum value. When current through it has maximum value. So for this, what happens? For this condition, this is essential for you all. XL is equal to XC. Now, what other changes will come? In the derivation that we were doing. Yeah, see, I naught was equal to what? E naught divided by this whole term. Yes, right there. So I naught was equal to divided by this whole term. So here what you will have, both these terms will be equal to each other. So Z is what? Z is equal to R, exactly. Z. So Z is equal to what? Under root R square plus either XL minus XC or XC minus XL whole square. No matter right now. Here XL is equal to XC. So put it in any manner. Z will be equal to what? Under root R square plus XL minus XL square, which makes it under root R square, which is R. So Z here is equal to R. Now, had you known this condition, you wouldn't have a need to solve it. As soon as you see this condition, directly assume that Z is equal to R. No need to perform this calculation. Directly you will get Z as 45. Got it? Here Z is equal to what? R. Resistance. Here the impedance is minimum. Now, obviously, see, when this will be less, then only you will get the current more. No. Resistance, when the resistance will be less, then only you will be getting the current more. So here in this condition also, if Z is equal to R, this means impedance is minimum. This means impedance is minimum. That's why current is maximum and you are getting the resonance condition. So what exactly is this resonance condition? Is when the current is maximum. And for the current and voltage to be in the same phase, current in the circuit has to be maximum. And for that, you have what? You have the value of Z as R. Why? Because XL and XC, why do they become zero? The reason is that for maximum, see, current becomes zero if omega is zero and omega is infinity. So maximum value is possible when only omega L minus 1 by omega C is 0. XL minus XC comes out to be 0. Then only, your current will be having maximum value. This is what? This is the least resistance. Least resistance, maximum current. So you can have this value, you can have this value in order to obtain this value. Now, one thing you have is frequency of LCR circuit that I'll just tell you. It's easy. Frequency of LCR circuit, no. Not LCR circuit, frequency at the resonant condition. Natural or resonant frequency. This is basically omega is what? Omega is 2 pi nu. Let's write it as R to show that it is at the resonant condition. Omega R is equal to what? 2 pi nu R. From here, this will be equal to what? See, omega L minus 1 by omega C, both are equal. Rewrite this. XL is equal to XC. Omega L is equal to 1 by omega C. From here, omega square will be equal to LC, omega will be equal to 1 by under root LC. Now if you put, this is omega R. Now put it here. Frequency at the resonant condition is what? 1 by 2 pi, and then value of omega, that is omega by 2 pi. No, so this becomes under root LC. This is the natural or resonant frequency. Questions I'll not do in today's class because so much time is not left. We'll do it in the next class only. Some of the characteristics also we'll do for series LCR circuit. We'll revise this. So just come and revise when you will come for the next class. You have the next class now on Monday. So before Monday, revise this during the weekend. I'll give the assignment also. Few questions only I'll give. So this is known as the natural or resonant frequency. This is which frequency? When current has its maximum value, when the series LCR circuit is at its resonance. And this derivation is very easy. Just remember this step. All right, class. Now note it down. Resonance condition.